week we are doing 10.4, Anova. Anova stands for Analysis of Variance. So last week we did a one-way Anova, and this week we are learning a two-way Anova. Let's start with our PowerPoint. Okay, so our PowerPoint can be found in Blackboard, and remember, I typically do not use the PowerPoint from Pearson to give you extra examples. Let me see. I don't think that's it. Hold on. Before I share the PowerPoint, I wanted to show, if I can find it, here we go, what you should be looking for in Blackboard for this lesson. So let me share Blackboard first. Here we go. Okay, so I'm in Blackboard and I went to course content and your weekly folder, week 9. And if we look inside here, you have your Pearson PowerPoint, which has good examples in it. Most likely doesn't give you full solutions. That's what's I don't like about them. There's wonderful videos here on how to do a one-way ANOVA in Excel and how to do two-way ANOVA in Excel. And then I have the lecture PowerPoint I'm lecturing from and an Excel file that you'll need to upload into Rguroo when we get there. Okay, now let's get started. So if we're talking about a two-way ANOVA, we are really talking about a randomized block design. So the purposes of doing this is to help alleviate some of the confounding variables or the variance that comes along with this. Okay, so the purpose of randomized block design is to control for potentially confounding variables in a research experiment. Suppose a nutritionist is interested in comparing the average weight loss for 3 different diets: a banana diet, a cabbage diet, and a grapefruit diet. 2 of those sound disgusting, but I don't even know if I want to be on any kind of straight food diet, but interesting. She has been funded to use 9 people in the studying these diets. One approach in designing this study is to randomly select 9 people and then randomly assign 3 of them to each one of the 3 diets for 6 months. We could then compare the average weight loss for each of the diets at the end of that period using the F test that we used and described in section 10.3. This type of design is called a completely randomized design. Although this may be perfectly reasonable approach, it does have shortcomings. So essentially, if we just randomly selected 3 out of the 9 people to do the banana diet, 3 out of the 9 people to do the cabbage, and 3 out of the 9 to do the grapefruit, that would be a one-way ANOVA. We would just be comparing the 3 groups. But for example, what if all the people selected to try the banana diet were at least 100 pounds overweight, whereas all the people selected to try the grapefruit diet were only 10 pounds overweight? Well, we did a completely randomized design, so it's very possible that the distribution of overweight and how overweight someone is was not accounted for when we just randomly selected numbers 1 through 9 to put into each diet. So what can be done to reduce the effect of this factor, which affects weight loss, but which is not directly related to how well the diet works? So one approach would be to divide our study participants into several weight bands called blocks. So those people who are more than 100 pounds overweight, another block for people who are between 51 and 100 pounds overweight, and the last block would be for those who are 0 to 50 pounds overweight. Then randomly select people, 3 from each of the weight bands or blocks, to try each of the diets. Excuse me. And finally, compare the average weight loss of each of the diets for individuals in each of the 3 weight bands. As with the paired difference design, we gave up degrees of freedom when we block. So this is the paired difference design, and what they're saying is once we block them and we make them dependent, remember last week we were working with independent groups, hence that would be if we did a random selection of just any old 3 people out of the 9 into each one of the diets, that's independent. But since we are blocking, each diet has a related member, the person who is over 100 pounds overweight, 51 to 100 and 0 to 50, that makes them dependent blocks. Okay, so because our blocks are dependent, we must be sure that the reduction in variation among sample observations is enough to compensate for the loss of degrees of freedom. This type of design is an example of a randomized block design. Okay, in the following table, we get the data that was collected by the nutritionist for each of the randomized block design. So here we are, we have over 100 pounds overweight, and there was this is saying how much weight they lost. Let's see, it gets collected by the nutritionist. Guessing this is the weight that they lost. 25 pounds on average in the banana group, 45 pounds on average in the cabbage group, and 30 pounds lost in the grapefruit group. In the person who was between 51 and 100 pounds overweight, here are the average weights lost. It seems like there's the same pattern. To me, it looks like the banana diet has the least amount of weight lost, while the cabbage diet seems to be the greatest amount. But are they so different that we should say that one is working way better than the other? That's really the question that we're trying to ask. So before proceeding with the Anova F test, we need to verify the assumptions are met. If we recall from last week, section 10.3, the Anova procedure is robust against departures from the normality and equal variances assumption. For this particular example, though, we do not have repeated observations for each combination of treatment. We only have one for each treatment in each block. And blocks, so this makes it very difficult for us to verify these assumptions. And ideally, we would have to collect more data values in order to make those assumptions or to be able to determine those assumptions. So the nutritionist should actually collect more data in each cell of the table to verify those assumptions and to provide additional degrees of freedom for the test. We will demonstrate this procedure regardless using a simplified randomized block example nonetheless. So essentially what we're saying here is we don't have enough data to actually verify the assumptions, but we're going to proceed with caution and make those assumptions assumed, which we really wouldn't do in real life, but we have a preformed problem, so we're going to do this. Okay, so the assumptions that we either know or are assuming is that the treatments are assigned at random with blocks, and the sample measurements in each cell, treatment and block combination, are random samples that are independent of each other. Okay, so the blocks are independent of each other, but they're a dependent setup. How do I explain this? So the blocks, each person, the people who are in the over 100 pounds overweight are clearly independent from the people who are in the 51 to 100 and the 0 to the 50, because they are 3 different weight classes, and there isn't going to be somebody who is in the 100 plus block and the 0 to 50 block at the same time. But the block design is designed dependently because each diet contains a person from each one of the blocks. Okay, I hope that made sense. The measurements in each cell come from a population that is approximately normal, and this we just slapped assumed on it because we don't know that. The populations have approximately equal variances, also slapping assumed on that because we don't have enough data to measure that. All the cells have an equal number of measurements, balanced design. Okay, so we do know that, though. We were told that there is one patient per block per treatment. So now we set up our hypothesis. So for the nutritionist, the treatments of interest are the diets. Okay, so we are actually testing the diets and whether there is a significant difference between any of them. So the null and the alternative hypotheses are the same as they were with the one Anova F test. The null hypothesis is going to be that all of the average weight loss are the same. Okay, and the alternative is that at least one of them is different. And if you recall from last week, I even stressed that even though we find out that one is different, we don't actually find out which one is different. We just know that one is. So the assumptions, treatments are assigned at random within blocks, and the sample measurements in each cell are random samples that are independent of each other. The measurements in each cell come from a population normally distributed, which we had to assume. The variances are approximately equal, which we had to assume. And all the cells have equal number of measurements. We know that one. So now let's jump to, hold on, hold on. I'm going to jump to Rguroo. Here we go. On my little screening thing. And let's share Rguroo now. If I can find it on my computer. Where on earth did I put it? Nope, that's not it. Okay, that's strange. I literally cannot find the screen that I'm looking for. Oh, dirt. Okay, I got it. Sorry. Okay, Rguroo, here we go. So let's log into Rguroo. Remember, you need the Excel file that I posted in Blackboard under this week's course content, and you will need to upload that under data. So if you go to data, you go to data import, and you don't go to create. I mean, you could create it if you want to type it in. We've learned how to do that last week. But you're going to upload a table, not a data frame, a table, and choose your file. Make sure you've already downloaded the 10.4 file and click open and upload. Okay, I'm not doing it because I already have it in here. So when I click on it, I notice how it imports. Remember, it imports with the diet, what block it's in, and the weight loss number. All right, then we'll go to analytics. So if you need more time to upload, then you should pause this video now so that you have it nice and uploaded and you could follow along. And then we're going to go to analysis and to Anova, just like we did last week. We're going to select the data set. We are going to select frequency as the response variable. We're going to go to the two-way tab. Okay, we are testing for treatments, factor A, against their blocks, factor B. And we don't actually need any of these diagnostics or tests because we can't test for normality. We don't have enough data values. And the significance level was not mentioned. So if you recall, when the significance level is not mentioned, we default to 0.05. Click my preview button. And here is my output. So here is my F value, which really means nothing to us considering we don't have the critical value given to us from Rguroo. I still don't understand why Rguroo doesn't give us the critical value. I'm going to have to reach out to my creators for Rguroo and ask them if they can put that in, because it's kind of annoying. The F value is pointless unless you have the critical value to go with it. But here's the p-value. Now notice we have two p-values. We have a p-value for treatments and we have a p-value for residuals, or blocks rather. And the blocks p-value is significant. So they're saying that the difference between the weight loss for the person who's over 100 pounds overweight, 51 to 100 pounds overweight, and 0 to 50 pounds overweight is significant. There's a significant difference between those. But that's not what we were testing. We were testing whether the treatment, the diets, were significantly different. And that p-value is 0.0754, and that is larger than our 0.05 alpha level, which means that it is not significant. And therefore, we would fail to reject the null hypothesis with this p-value. And failing to reject the null hypothesis means that each one of these diets is stated to be approximately the same. So if I go back to the PowerPoint to see this conclusion written out. Okay. Our conclusion is that the test statistic we found was 5.2857. The critical value, if you used a table or a calculator, you would get 6.9. So this is less than that value, saying to fail to reject, but we'll be using this p-value, which is 0.0754, which is greater than our alpha level default of 0.05. So there is not sufficient evidence to conclude that there's a difference in average weight loss among the three diets. Okay, so that's the conclusion we can make. It looked as though the pattern was that the cabbage diet produced more weight loss, but it's saying that the difference between these block numbers, and these block numbers are not significant, although when comparing the weight loss horizontally among blocks, they are significantly different. So it does show that a person who is one of these weight blocks loses more weight on a diet than another, but that's kind of logical. So if you think about it, people who have a lot of weight to lose, they start a diet and they shed pounds very quickly, and then they hit a plateau at some point. And people who are slightly overweight have a harder time in some cases because they have to work a little harder to get that weight off when they're almost at their goal weight. Okay, but that concludes our presentation for today on two-way Anova using a randomized block design. And I will see you guys next week.